I never eat breakfast.
That's how you.
Okay, people, I've had more than one question. I've had more than one question about those properties that we talked about yesterday. And so I want to go over them in a little greater detail so that you can understand what's going on. Because once I explain, I think, the sum rule in a little bit better form, I think the others will fall into place in your mind and click, I hope. I'm talking about the bottom of page 61. And when we talked about it yesterday, I explained it in generalities. We had an f of x and a g of x and an L and an M, and then we talked about all of those things. But I don't think it sunk in very well with some of you. You don't think so either? Okay. Then let me slow it down a little bit. I'm not going to give you specific functions f and g unless it's necessary. If it's necessary, you still don't understand what I'm saying here in a few minutes, please speak up. We can do it, I can do it better, but I'm hoping that covering it this way will work out okay. Let's pretend, just for the sake of easiness to understand, let's pretend that the function f and the function g are both polynomials. Can you visualize, can you gather in your brain polynomials all together in a group and kind of understand what they are, polynomials? Polynomials never stop, they never have a break, they never have any corners. They're what we call very well behaved when you graph them. Okay, polynomials are well behaved. So are rational functions, except for they have asymptotes on occasion when the denominator is zero, if it is zero, not always. If there is one, it's an asymptote. So let's pretend for just a moment anyway that f of x and g of x are two different functions and they are polynomials. And let's pretend that, I'm just going to draw pieces of them. And let's say that we want to go figure out what's going on when x is 3. That's what we want to figure out. And so let's say that polynomial f is a parabola. It goes like this, and pretend just with me for a minute that that value at 3 for that right there on that, this is f, that value over here is 3. No, 4. We'll say 4. And that we have another polynomial g that comes down like this. Comes over here, polynomial, it winds around a little bit like this and comes down this way. This is g. And at 3, g has a value of, let's not just double it, let's say 7, just for the sake of not thinking there's anything strange going on here. Well, there is something strange going on. This is going on. So what we say then is that f of 3 is equal to 4, and g of 3 is equal to 7. Okay, those are things that you're familiar with, okay? Now, because these are polynomials and well-behaved with no breaks in them, no asymptotes, no corners, no weird things, no nothing, we could also say that the limit as x approaches 3 of f of x is 4. Because when you're on the function f and you are approaching 3 from either side, doesn't matter, you're coming in closer and closer to 3 from either side, you will land at a value of 4. So we're not interested in what happens at 3 when we talk about the limit. We're talking about what are you getting closer to as you get closer to 3, and the answer is still 4 because there's no breaks or anything, okay? And the limit as x approaches 3 of g is 7. So what we're saying now is that what this property is saying is, in this particular case, is if I add f of x to g of x, by the way, it's notation, sorry, that's supposed to be add. Funny notation. This actually means whatever f is, it looks like a parabola, and maybe this is a, I don't know, upturned 4th degree polynomial, possibly. If I add them together, that is, I take all the components of f and all the components of g and add them together, like terms all together, and create this new function called f plus g. This is notation that they use. It's a brand new function that is born from adding f and g together. Then what this property is saying is that f of g, f plus g of x, is 11. Because the two limits add together to make the limit of the new sum you add the limits to get the limit of this new function f plus g at 3. That's what I should have said. Which means that the limit as x approaches 3 of this new function is 11. Its value is 11, and as they approach it, it's going to be 11. You following me? So in a general way, if I have f and g, if I say the limit as x approaches c of f of x is equal to L, and the limit as x approaches the same c, it's going to be the same number like it was 2 over here, of g of x is m, then if I do something to f and g, like add them together, or subtract them, or multiply them, or divide them, or multiply one of them by a constant, then its individual limit you do the same things, like with the sum that I said, the limit as x approaches that same c of f of x plus g of x. Most people like to see it written that way better. It's written this way as well. It's going to be L plus m. And if you subtract, it's going to be L minus m. And if you multiply, it's going to be Lm, the limit. And if you divide, it's going to be L over m, so long as m is not 0. And if you take k, not divide here, if you take k times f of x here, it's going to be k times L, its limit. And if you take f of x and raise it to a power, r over s, it's the limit of this new function is going to be L to the r over s. That's what they're saying. You do these things to the functions, the limits do the same thing. Yes.
What other have us do like g times f instead of f times g or is
Same. It's just m times L, which makes no difference because our multiplication is commutative. If you do g minus f this way, then it'll be m minus L. If you do over here on the division, if you do g divided by f, then it'll be m over L is its limit. Y'all see what's going on? It's a fairly straightforward property, but if you only, I guess, explaining it only with letters left you kind of wondering. Does that help you at all? Yeah? I hope? Okay. All right, so that's that property box at the bottom of page 61 and the very top, it continues at the top of page 62. All right, so now this next part is going to seem, and it is kind of, sort of, going to seem really dumb. It's going to help you get points on quizzes and tests, though. The reason why it's going to seem dumb is because it's so easy. However, it's fairly important. That's nice when things are important and also easy. Okay, so now what we're going to do is we're going to say if we have a polynomial or a rational function. Now, I had you try to visualize all polynomials. Polynomials that are even, as you know, you know some characteristics of them. If the polynomial has an even degree, then it will either start high and end high or start low and end low, depending on the sign of its leading coefficient. Right? You know that? And if it's odd with a positive leading coefficient, it'll start low and end high. If it's negative, leading coefficient will start high and end low if it's an odd degree. Right? Remember all those kinds of things? Well, polynomials are they just wind around and they just go forever. Eventually they end up going somewhere and staying there. But they're really well behaved. We also have pretty well behaved, as I said before, rational functions. And a rational function, you remember what the word rational means in math? When we have the word rational in the title of a section?
It doesn't like list on it endlessly without repeating.
What?
It doesn't list on endlessly without repeating.
Possibly. I'm not talking about rational functions. I'm just talking about the word rational. And I think I follow what you're saying. But when you see the word rational in the title to anything mathematical, it means you're going to be discussing fractions. Because it is the fractions that separates the integers from the next set of numbers called the rational numbers. It is the fractions. When you introduce fractions, now you're talking about rational numbers, not just integers. So the word rational means fraction. And when we talk about rational functions, a rational function is a polynomial divided by a polynomial. So it isn't just a function over a function. These actually have to be polynomials to be a rational function, but it's a fractional made up of divide in the middle of it. And rational functions have asymptotes where the denominator is 0. or at least a whole. Does this sound familiar at all?
Kind of.
Yeah.
A little bit? Okay. We'll talk about those as we go along, but and as a group, that's just two types of things, polynomials and rational functions. You'll see at the bottom, I skipped example 3 on purpose. I'll come back to it in a minute, it's kind of dumb. But page 62 at the bottom, it says polynomial and rational functions, theorem 2. If you have a polynomial function or a rational function, and you wish to evaluate its limit at a certain point, a certain x value, plug it in. That's it. You just plug it in. It's called evaluation by substitution. Look at the top of page 63. Example 4 says, find the limit as x approaches 3 of x squared times 2 minus x. Now, believe it or not, that is a polynomial, because if you distributed the x squared, it would be a third-degree polynomial, yeah? Okay, so that is a polynomial. We wish to evaluate that polynomial's value at 3, and since they're always well-behaved, its value at 3 and the limit as you approach 3 have to be the same thing. Plug it in, you get -9. Just that easy, just a straight-up plug-in. Same with rational numbers, so long as the thing you're limiting it to doesn't cause the denominator to be 0. And in this example, it doesn't. It causes the denominator to be 4 by simple plugging it in. So you plug it in the numerator for x, plug it in the denominator for x, clean it all up, reduce it, get 3. So what we're saying is that you can often evaluate things by just simple plugging it in, especially polynomials and rational functions, with one exception, as long as what you're limiting it to does not cause the denominator to be 0, because that would be an asymptote or a whole, and all bets are off there. So as far as plugging it in, just substitute.
Or would you put no solution?
No, there's ways of evaluating limits even though they may not exist at the actual value. We'll get there.
Oh,
Yeah, that's where it gets to be calculus-y. This is just algebra 1. This is dumb. Just plug it in. If everything's behaving well at the place you're plugging it in. And it will on a polynomial every time. And it will on a rational function every place except an asymptote for whole. Okay? So if I were to go back to example 3 for just a minute, there's another polynomial and another rational function, but we're approaching c, not a number. So what do? You replace every x with c, and that's it. Because you can't do any more with it than that. Nothing will combine. So it seems, like I said, it seems kind of dumb. All you did is turn x's into c's. Well, that's how you evaluate a limit for a polynomial or a rational function. Just plug in what you're limiting. Clean it up if you can. Don't if you can't. Leave it. Okay, moving on. Example 5 is like turning a page in a book or getting a new book. This is going to be different from what we've discussed so far today. Example 5 says, using the product rule, which we discovered over here was number 3 in the properties list. We're going to use it in a rather clever way. Okay, we're going to try to find the limit as x approaches 0 of the tangent of x over x. This is a rational function. Well, it's not really a polynomial over a polynomial, but it is a fraction. So we're going to do the limit as x approaches, what did I say, 0? Of tangent x over x. And the first thing you should try is direct substitution. And as soon as you try it or even analyze it even for a second, you realize it's not going to work because it causes division by 0. It's not going to work to just simply plug it in. So we got to get clever now. And this, remember I told you the title of your book was Algebraic, Graphical, and Numerical? Maybe not in that order. But we are going to tackle this one algebraically, which means on paper, using our brains, and got to be clever. So here goes. I obviously can't just plug it in. So I've got to fall back to my the trigonometry that I know and see if I can do something else with this. And that first thing that occurs to me is, does anything occur to you?
Sine over cosine.
Rename the tangent. That's what I would do. So we rename the tangent. So I'm working on manipulating this. I'll come back to the limit in a few minutes. But I'm working on manipulating this. So this is sine x over cosine x. This is over 1. So this is times 1 over x. Is that okay? So I'm inverting and multiplying. Okay, so what I have now is sine x over x cosine x. I just chose to put the x on the front so we don't confuse it with the fact that this is not x squared. The x times the cosine of x, yeah? So this is just a rewrite to clarify a little bit. You look at that, you go, okay. So If I do direct substitution now, I still have division by 0 because I still have to plug 0 in for x. Well, that was nice. Now comes the clever part. We're going to rewrite this part, this piece right here, as the sine of x over x times 1 over the cosine of x. Can we do that? It's kind of doing fractions backwards. Usually we have something like that and we get them together into a single one, but I could pull them back apart. Isn't that product this? This allows me to consider two pieces separately because of the product rule. If I could find this one's limit, and if I could find this one's limit, then I could multiply the two limits together, treating these as two different functions, right? In other words, this is what I'm saying is what the property tells me I can do if I split this up is finding the limit of this whole thing, which has been rewritten as this. I could find the limit as x approaches 0 of sine x over x and multiply that by the limit, whatever that is, the number that's the limit as x approaches 0 of 1 over cosine x. I could treat them separately. Well, what is this limit?
Nothing.
Yes, it is. And you're going, oh, I can't plug it in. We figured this out yesterday. So I told you it would be a very, very important one. And you're right, it's 1. Remember I told you to box that up yesterday and remember it? The author didn't make a big deal out of it. I thought he should. Remember I showed you, I showed the person I'm recording this for and I showed you guys and I said, remember this, it's important right here. Did? We have a value for that. We didn't actually figure that out algebraically, but we did with our calculator. We discovered that its limit, it doesn't exist when x equals 0, the actual value, but its limit as you approach 0 is 1. Do you recall? Yeah. It's kind of an important thing. It rears its little head every once in a while, and it's nice to remember that limit. So this right here is like the L I was talking about, and that's 1. What is this limit? Can we evaluate? First, you should always try to evaluate it by direct substitution. Can you evaluate that by direct substitution?
Yeah.
Yes? This doesn't cause division by 0. What is the cosine of 0? 1. This is m. So what is this ultimate limit? 1. Now you could have done this graphically as well, but I wanted to show you an algebraic solution. People go, well, I could have seen that on my calculator. Yeah, you could have. The objective is not to find this limit, it's to find it being clever. This is clever. Okay, so if you actually graph this on your calculator, you can if you want, or you can just look at the graph of it that is provided in the book. The graph is provided just to the left of example 5 on page 63. It's got asymptotes at pi halves, where we would expect, but it is... If you can see the scoop that comes down and goes through at 0 appears to hit the y-axis at 1. Doesn't actually hit there. There's a hole there. You won't be able to see it with your calculator, but there's a hole there. So f of 0 is undefined. But the limit as we get close to 0 is 1. This is the algebraic way of showing it. You with me? This limit right here shows up and I shouldn't say all the time, but when it does, it shows up enough that it's nice to have that memorized. That limit is 1. Okay, so moving on, look at example 6. This one actually says use a graph, and that you're using the graphical portion of our study of calculus. It says use a graph to show that the limit as x approaches 2 of x cubed minus 1 over x minus 2 does not exist. And so you would graph it and put it in a reasonable window so you can see what's going on when x is 2. Obviously, you can't do it by direct substitution because plugging 2 in gives you division by 0. So you have to figure out some other way to handle it. You could be clever, I suppose, although it's kind of hard to do in this one, what we're talking about, but you could graph it, and it tells you to graph it. It's not only giving you permission, it's providing you with a way to get after it. So you graph it, and you get that graph, which is next to example 6. Look what happens when x is 2. To the left side of 2, we're not getting the same thing. Make sure you scoop things in parentheses. Numerator and denominator have to be in parentheses.
You gotta readjust your window. Well,
Yeah, this
gets negative 100.
Notice the window that they've got here goes from negative 10 to 10 on the x's, but it goes from negative 100 to 100 on the y. Sometimes you gotta zoom out to see what's happening at 2.
Sorry.
Okay, now it looks like the one in the book, right? So sometimes you gotta adjust things and manipulate the window a bit. But notice what's happening at 2. That's the thing I wanna focus on. Has everybody got a graph so you're no longer working with your calculator and you're ready to focus on the calculus? Yeah? Right at x equals 2, something bizarre happens. We expect that because x equals 2 makes division by 0 in the equation. But what happens is, to the left of 2, the graph goes down. As we approach 2 on the left side, it goes to negative infinity. If we are on the graph to the right of 2, and we get on that, we come down that little scoop when we head towards 2, getting closer and closer and closer to 2, we end up going, because it doesn't settle on a number. The limit from the left, coming in from the left, and the limit coming in from the right does not settle on a number like the previous one. Then the limit doesn't exist. We don't say it's undefined, because from the left and the right it is defined. We can tell what it does, but the limit itself doesn't exist because it does not settle on the same value from the left and the
So
right.
if those both went down to negative infinity, would the limit exist?
Then we would say the limit is negative infinity. Even though
Okay.
that's not a number, we would say that, and that would tell us that both sides of it go to the same thing.
Okay.
But this one doesn't exist.
So how come the one four exists? What's up?
Because we're approaching 0, and the limit as we come in from the left on this, I'm talking about 0 right here, this is the graph of it, so these parts don't matter. As I'm coming in closer and closer and closer to 0, I'm getting my y value closer and closer and closer to 1. Even though right here there's a hole. I don't care what happens at 0, the limit happens as I get close to 0. And the y value is getting closer to 1 as I get closer to an x of 0. From the right side, it's also getting closer and closer to 1. Therefore, the limit is 1 because it settles on the same number from the left and the right. You see what I'm saying? Oh. Anyone else have a question about that? Limits are weird till you get a handle on them, and then you look back, a week from now, you'll look back and go, oh, I get it. But it's a hard thing to adjust to right at first. Okay, so now we're gonna talk about one-sided and two-sided limits. We're gonna talk about what happens as you come in from the left and as you come in from the right. And we're gonna use the greatest integer function to play with that idea a little bit. So turn to page 64. Do you all remember the greatest integer function, what it looks like?
Yeah.
Would you like to explain a little better why it does what it does?
Yeah.
All right, hang on a minute. Let me put this up here so I can point to things.
It's that boy.
Okay, so right here on this very first one, this is 1, 2, 3, and 4. And it's called the greatest integer function, so we're dealing with integers. Right here at 0, if we go out to here, as we get to 1, it takes on the same y value until we get to 1. And right at 1, there's a hole, and it jumps up to here. And I'll show you why. I'll show you how this thing is interpreted in just a minute. And even give you an example where it's useful. Okay, and then we jump up to, it takes a jump right there up to here and stays the same value until we get to 3. And then at 3, there's a hole, and then it jumps up to 3 and does it again. So this is a few branches of this. And this one over here starts here, comes down to -1, starts here with a solid one, comes over here and there's a hole. And down to 2 here. So it's solid here, comes over here and there's a hole. Is that a function? What's its domain? All real numbers. Every single number is hit. Every single x value is hit somewhere. What's its range?
Every integer.
Yeah. Its range is the set of integers. Nothing, no fractions in between are hit. There's a desert here. Okay, and it looks like this. It depends on the book you see, but it looks like this. F of x equals the greatest integer x. In your calculator, it looks like this. And what it means is that whatever you are trying to evaluate, for example, if I was trying to find f of 1.2, then you fall back to the integer that belongs. You fall back to the integer just before this. That's 1. 1.2 is right there. What's its value? 1. So what is f of 1.9? 1. What is f of 1.99993? 1. What is f of 2? 2. That's where the jump occurs. That's what the greatest integer function means. It means whatever you are functioning, whatever x value you're functioning, fall back to the integer just before it. So even if we do negatives, if I do f of negative 1.3, the integer below that, to the left of that, is negative 2. And look, negative 1.3 is right there. It's negative 2. You go to the integer just before that on the number line. And that's the y value that we'll have. You following? This can be useful for things like figuring out how much it's going to cost to mail something. You take a small package in, and it will tell you that between 0 and 1 pounds, it'll cost you, or 0, yeah, we'll say that, we'll just pretend. 0, it's generally with letters, and it has to do with ounces, so we'll stick with letters. Between 0 and 1 ounce, it costs you 58 cents to whatever it is. I don't even know what the price is now, to mail it. You stuff more than that in, and it weighs 1.2 ounces, now it's going to cost you an extra dime. So now we're up at 68 cents. If it's 1.8 ounces, it's still 68 cents. If it's 1.9 ounces, it's still 68 cents. Get 2 ounces, now you've jumped up another 10 cents. You know what I'm saying? Yeah, that's how stuff like this. And for instances like that, and it shows up more often than you think, as the greatest integer function to graph it. Now I want to talk to you about limits. I'll leave that up there. So consider this and what you know about limits so far, and see if you can evaluate what is the limit as x approaches 3.3. Three, by direct substitution of int x. Isn't that true? You go out here to 3.3, you go up here, that's at 3. Okay, direct substitution, that was easy. So what's the limit as x approaches negative 1.2? Is it negative 2? Now what is the limit as x approaches 2?
2.
And the answer is, it does not exist. Because the limit from the left side of 2 and the limit from the right side of 2 are not the same number.
You just said that.
Now. At 2, what is the value?
2.
We don't care. But you're right, it's 2. But we don't care when we're looking at the limit. We never care what happens at 2, ever. We care what happens as we get closer to 2 from either side.
Oh, and then it goes outward jump.
Yeah,
So as we get closer, now this is the way we write this. So we're asking ourselves, what is this? And the answer is, I've already told you, it doesn't exist. But here's why. Because the limit as x approaches 2 from the left, we put it in the exponent position, but it's just a sign, means coming in from the left of integer x. I'm getting tired of writing it like this. Is what? What happens? What's the value as we get closer and closer to 2 from the left side of 2? So here's 2. We get on the graph to the left side of 2. That's this piece right here. So we're on this one like a little bug, and we're getting closer and closer and closer and closer to 2. What are we getting close? What's the y value that we're getting closer to? 1, and it has been 1 all along. And so this is 1. What happens as we find the limit as x approaches 2, and we use a plus sign in the exponent position? I know it's not an exponent, it means from the left and the right of int x. What is that?
2.
It's 2?
Yeah.
Then we say, since 1 does not equal 2, the actual limit, without regard to left or right, the limit as x approaches 2 of this function, and I don't write equals, you write does not exist. Because it's not settling on the same number from the left and the right.
Do we have to write all that down when we're answering?
If it asks you to prove it, if it says, what's the limit, and you say it doesn't exist, and it says explain, then yes. You have to say the limit from the left, and you can use the words, you can write it out in words. The limit of the function from the left of 2 and the limit of the function from the right of 2 are not the same number, therefore it doesn't exist. You gotta write it out. You gotta indicate why you believe this is a DNE. Okay, because left and right limits are not the same. So anytime you are in this function, anytime you are taking a limit at an integer, it won't exist. Because the limit from the left and the limit from the right are not the same. Okay? That's what theorem 3 says. Take a look at it, see if you can understand it better now if we read it. It says a function f has a limit as x approaches some value c, if and only if, which means it goes backwards and forwards if you'll remember from geometry. It means it's a biconditional statement. If the right hand and left hand limit exist at c and are equal. So we say, if we know the limit exists and we know its number, then that means that the limit from the left and the right are the same number, that number. But if the limit as we approach, if the limit from the left and the limit from the right are different, then the actual limit doesn't exist. Okay. 2 more things. I only have an hour left today, but I think we're going to be able to get through. This next one, the author drills and kills you on, and thank goodness, well, maybe not really too bad. Sort of he does in the exercises. But this is a really fun one. I want you to have your eyeballs on the graph to the left of example 8. First of all, is that a function?
Yes.
Or the amount of it that we can see, it is. And that's the only part we're interested in, is the part that they drew. So my question to you is, now I'm going to ask you a whole bunch of questions. See if you can answer them, and don't blurt it out. Give everybody a chance to think. My first question is, what is f of 2? Anybody? 2. At the value x equals 2, the y value is 2. I'm not talking limits. I'm talking actual values. Do y'all see that spot? See the dot up there? What is the limit as x approaches 2? It is 1. From the left and the right, it's getting closer to 1. But exactly right at 2, it jumps. So the limit is different from the actual value, and that's okay. Because we're not interested. When we ask about limits, we're not interested in what happens at 2. So here's my next question. What is the limit as x approaches a half? What's the y value as x approaches the x value of 1/2? 1/2, because you can tell the slope of that line is -1. Because it starts at 1 and it ends at 1, if you will. And so it's got a slope of -1. It's going to be a half. What's the limit as x approaches 3? 2. What is f of 3? 2. That's an indication that it's continuous there. If the limit and the value are the same. We'll talk about that later. Don't worry. Don't panic. Okay, the next question is, what's the limit as x approaches 1? The limit as x approaches 1 does not exist. What is f of 1? 1. What's the limit as x approaches 1 from the left?
0.
Good. What's the limit as x approaches 3 from the left?
2.
What's the limit as x approaches 4? This one you say, listen, in order to answer it with as much, like spilling out as much knowledge as you have onto the paper, to answer that question you say, we don't know, but from the left it is 1. We don't know what happens to the right, nor do we care. But because we don't know what happens to the right or care about it, we can't tell what the limit is. But we can tell what the limit is from the left. So, what's the limit as x approaches 0? Somebody give me a good answer to what's the limit as x approaches 0?
From the right.
We don't know,
But from the right, it's 1.
but from the right it is good. What is f of 0?
1.
1. Okay. So do you think you kind of understand this crazy busted up graph and how to answer the questions? I hope. I didn't hear responses from all of you, but I hope you picked it up. One more concept, and that is called the sandwich theorem.
Yes.
And the sandwich theorem does not apply very often, but when you need it, it is very helpful. It does not show up very often. Again, because the author and I want you to know how to use it, it will be showing up on a quiz and likely a test. But in reality, it isn't used very often, but when it's needed, it sure is handy. Here's the idea. I have a function f, well, you can see it in your book. I have a function f and a function g and a function h. Look on the top of page 65 in the upper left corner where you've got some blue and red going on. See it?
I see it.
First of all, notice that we are interested in the value when x is c. And all of these things seem to coincide with the same limit, L, at c. They're all over the place, other places, but at c, they all seem to have a limit of L. Now, let's pretend for just a second that f, which is the blue one, is undefined at c. It's got a hole there. Can't tell what the limit is at c. Can't tell what's happening as it comes in because you can't do it by direct substitution. You can't tell what it is. But you can tell algebraically what h's limit and g's limit is at c. Since f, the blue one, is sandwiched in between the red ones all the time, then the limit of g and h at c must also be the limit of f at c. Since they're all together and have the same value, they're sandwiched. And we could evaluate h and we could evaluate g, and since we know that f is between it all the time, then surely f's limit there is the same because it's sandwiched between two we can figure. You're going, yeah, it's kind of obscure, kind of makes sense. This is how it works in practice, and it's when you actually see an example, first example is still not very easy. So here's what we're doing. Some people never do get this; they just miss it every time it's on a test. It's an interesting thing, and I will try to talk you through it in a sensible way so that when you go to use it, hopefully you'll remember how. But this is what we're trying to limit. The limit as x approaches 0 of x squared sine 1 over x. It says show that it equals 0. So we know what the limit's going to be. We're not actually trying to find the limit. We're going to show that it actually is using the sandwich theorem. Before I begin, and by the way, this is the only time I've ever seen this used on any test that it's ever been written on. There's always either sine or cosine involved. Now, that's important because the first piece of the sandwich, the first layer of the sandwich, the peanut butter and jelly that's going to be right next to each other, sandwiching things. You have to understand that sine and cosine, as long as there is no amplitude, remember amplitude? As long as there is no number that is an amplitude, will always be trapped between -1 and 1, no matter what it is you're signing and cosine. I don't care what you sign or what you cosine, it's defined for all real numbers, and its range will never be less than -1 and never more than +1. It makes no difference what is sitting in this position. Don't look at this, just look at this. It makes absolutely no difference at all what you put right here. This thing will always be trapped between -1 and 1, its values. You with me? Same for cosine.
I have a question. So if the amplitude was something different, would it be between?
Yeah, if it were 3 sine x, then it would be trapped between -3 and 3. Okay. And you're looking at that and go, but that's an amplitude. No, it isn't. It's the product. This is a product of two functions. And I want to talk about just this one for a minute. I'll bring him home in just a minute. This guy right here, no matter what you put, the y value will be trapped between -1 and 1. Now, if you put 0 in here, you're trying to sign something that's undefined. Nevertheless, it will be trapped between -1 and 1. Okay, so this is how we start using the sandwich theorem. We take this guy right here and we take the sine or cosine aspect of it. And we trap it between the things that we know must be true. Any value that you can plug in for x and evaluate will be between -1 and 1. Do you agree?
I have a question. What if it was 3x squared sine x 1 over x? Would that affect the amplitude of the sine?
If it were x squared times 3 sine 1 over x, then this would be -3 and 3.
Okay, but not if it was 3x squared sine.
I would still, even if you had this. No, if it were sine 3x squared, what?
If it was like 3x squared times the sine of 1 over x.
Then we'd bring the x squared and the 3 in just a minute. You'll see how it's gonna work. But even if I had this, I would still start with this between -1 and 1, and I keep building all these extra things in. That's what sandwich theorem does. So this is a place to begin. This is where you always begin, because this is a fact that everybody who's ever studied trig knows. This is always between -1 and 1, okay? Turn my phone off just a minute. So we start out with a fact that everybody who's ever studied trig knows that that's a fact, and we build on that. So watch how this goes. This is interesting. The only difference between what we're actually trying to limit and what we started out with as a fact is this x squared. And x squared is always a positive number, right? Always a positive number. So, well, or 0 if it's 0, but we're not plugging it directly in. So it's something other than 0. Okay. So the reason I bring that up is because I'm now going to multiply all pieces of this known inequality. I'm going to multiply each piece of it by x squared, and I know it's not going to flip these signs because I know what I'm multiplying by is a positive. That's why I bring that up. So this is going to be -x squared less than or equal to x squared sine 1 over x less than or equal to x squared. That's multiplying this by x squared, this by x squared, and this by x squared in an attempt to get to where I'm trying to limit it. You with me there? Now you still cannot evaluate the limit in here by direct substitution because you have division by 0 right here after the sign. So you can't plug it in. But since this piece is always, no matter what, is always sandwiched between these two parabolas, then I can limit this one at x equals 0. That's an easy plug-in. I can do the limit as this one goes, x equals 0, and that's an easy one. If these turn out to have the same limit as 0, and they will, then surely this one is 0. So this is the next step. Once you build it up so that this is the function that you're trying to limit, and you've built it up on all 3 pieces, then you do this over here. You take the limit as x approaches 0 of -x squared, and you know what that is, direct substitution. Yeah? Take the limit of the right side as we approach 0 of x squared. That's also 0 by direct substitution. Since these are the same, and this is always in between them, this one's limit at 0 must be 0. This is how you write it. Therefore, the limit as x approaches 0 of x squared sine 1 over x is 0 by the sandwich theorem. That way you're using the concept of sandwiching. This is the sandwich, this is the bread, this is the junk in between, and its limit's got to be the same as this limit at 0 if they're both the same number.
Is this like, is that the official name of the theorem?
Yes.
So like, what's it called?
Yes. Some books call it the squeezing theorem. This book calls it the sandwich theorem. So did my book when I studied it. It's called the sandwich theorem. You want to see another one? Just to see how it's put together?
Yeah.
One more? Okay, I'm going to make this one up. It's going to be tougher. I want to show that the limit as x approaches, I'll go ahead and say 0 of x, let me say 3x to the 3rd. No, I can't do x to the 3rd. I have to be an even number. 3x to the 4th cosine of 1 over x squared plus 2 equals 2. I'm going to show you.
Oh dear.
Guys, this isn't even that bad.
Okay, so we start out with the fact about the trig that we know. Because direct substitution causes us problems. You see it?
Yeah.
Okay, so we start out with the fact that we know, which is cosine of 1 over x squared, and we know that will always be between -1 and 1.
Wait, why does it cause us problems?
And no matter-
Because if you plug 0 in right there, you're cosigning something that's undefined, you can't do that.
Oh, yes.
Is everybody clear on this first statement?
You can cosine.
That's a fact that we know because we've studied trig and we know cosine is trapped. No matter what sits back here, whatever the angle is, the cosine of it will be between -1 and 1. Now we start building this up. We start here, and the next thing I'm gonna do is I'm gonna multiply by 3x to the 4th all the way through. Okay with that?
No.
I'm not ready to take the limit yet because it doesn't quite look like what I'm trying to limit. So now I gotta add 2 to everything. See it?
Yeah, but then you have that 2 on the end. Either equals 2. Oh, because we know that's what the limit, never mind.
As long as you just keep building it up from the trig piece of it, you do the multiplying, you do the adding, whatever it takes in order of operations until this looks like what you're actually trying to limit. And you do it to every piece. We still can't take this limit by direct substitution. I mean, it's the same thing. We couldn't before, but we can these. The limit as x approaches 0 of 3x to the 4th plus 2 is 2. By direct substitution. These are polynomials. The limit as x approaches 0 of 3x to the 4th plus 2 is 2. Therefore, the limit as x approaches 0 of, 3x to the 4th cosine of 1 over x squared plus 2 is 2 by the sandwich theorem. So what we're doing is exploiting the fact that polynomials limits can always be found by direct substitution. These are polynomials here on the ends. This is a mess. But these are polynomials, so by direct substitution, we discover they have the same limit at x equals 0. Therefore, the junk in between must have the same limit because it's always in between them.
So is this just to prove it? Because you like at the top it says it's equal to 2. So
Yes.
it's just to prove
When it says show that or prove that, that's what we're doing. It tells you what the limit is. It says show it. Why do you believe that's true? Give the algebra, give the reasoning behind this. And it's the sandwich theorem that lets you do it. Okay. The sandwich theorem, like I said, almost exclusively involves sine and cosine because we can always trap those between -1 and 1 to start with.
Will there be a case where it doesn't have what it's already equal to and we just have to figure it out?
If it said find this limit, you could also find it with the sandwich theorem. If it didn't tell you what it was, you could still do it, starting with the cosine, and just build it up until you find the limit that it approaches on both sides. Now, it doesn't work if this one approaches 2 and this one approaches 8. They have to both approach the same thing. That's the reason why the sandwich theorem is quite limited to its uses, but when that's what it calls for, it's very useful.
And what would you put if they don't end up equal?
If they don't end up equaling each other, say, I can't determine this, at least not with the sandwich theorem. Okay, finally done. I hope you understand it well enough you can get after it, but we've got a few minutes left to get started. If you've got any questions you ran into yesterday, bring them up or whatever, but there you go. Tomorrow, I will just let you work on this. We'll move on Thursday.
Oh, so when is it? That means number 12 is gonna be,
There you go. Bye.
yeah.